And chords, we're going to just, the first section is mainly just terminology. So let's start with number 1, circle. So a circle is the set of all points in a 2-dimensional plane. 2-dimensional means length and width, so it's flat. And it is, all these points are equidistant from a center point. So all the points on a circle are the same distance to the center, no matter where on the circle you are. There are an infinite number of points in a circle. The edges of a circle look solid, but they're actually a collection of infinite points. So close together, you can't see spaces in between them. So it's an infinite collection of points. The center point provides location, but is not part of the circle itself. So the center is used to designate where the circle is. It is not mathematically part of the circle itself. Okay, so center point. Center point is a point in a circle that is equidistant to any point in the circle. A circle is often labeled by its center point. And we use a circle with a dot in the middle. That means circle. And then you name the middle. So circle O is a circle with the center point being O. So it gets named by its center. That would mean that this one is circle A. This one is circle O. The one at the top is circle C. You'll notice that it's capitalized. Names of circles are capitalized. The center itself is not part of the circle. It only provides location. All right, number 3. Radius, lowercase r. Radius is the distance from the center to the edge of a circle. A radius is a segment that can be measured. So if I draw any segment from the center to the edge, that would be a radius. And it doesn't matter if I draw it there or if I draw it here, it's still a radius. If I call the point where it hits the circle X, this is actually segment AX. That's measurable. Okay, example. I want you to draw 3 radii, that's radius plural, in circle O and label their points. It's supposed to be points of intersection G, H, and I. So go ahead and do that on the circle. Draw 3 radii and label their points of intersection G, H, and I. All right, your 3 radii might not look like your neighbors, and that's okay, because any segment from the center to the edge is a radius. And we can name their points of intersection G, H, and I. And because these are radii, they're all congruent. So G to O, O to I, O to H are all congruent to each other. All right, number 4, diameter. Diameter is a segment that passes through the center point of a circle. It has endpoints that lie on the circle. A diameter is the same length as 2 radii. So diameter equals 2 times radius. So if I draw on this circle up here, a line that goes from the edge of the circle through A to the edge of the circle, that is a diameter. If I call the points of intersection C and V, we can say that the length of CV equals 2 times the length of AX, because the diameter is 2 times the radius. If I divide both sides by 2, I end up with the radius equals 1/2 of CV, which is the diameter. So 2 radii equal a diameter. All right, flip the page. Okay, another example. If the radius of circle L is 45 meters, what is the length of its diameter? So diameter equals 2 times the radius. So my diameter would be 2 times 45 meters, which is 90 meters. All right, this is a question I pulled off of a SAT practice question. It says circle A has a diameter of 12 centimeters. Circle B has a radius of 7 centimeters. Circle C has a radius of 5.5 centimeters. Find the length of XY. And I have to put this on here. X is this point. Y is that point. Okay, so let's use some logic. If A has a diameter of 12, that's all the way across. It has a radius of half of that, which would be 6. If B has a radius of 7, which is halfway across, then all the way across would be 14, or 7 and 7. If circle C has a radius of 5.5, then the diameter all the way across is 11. So XY is 6 plus 11 plus 7 plus 7. So the length of XY equals 31 centimeters. Remember that length means no bar. When you're referring to segment XY in any other context, it should have a bar on it. But because we want the measure of XY, we leave the bar off. That's something we learned the first week. Okay, intersecting lines and segments. Here we're getting into some new vocabulary. Number 1 is a chord. A chord is any segment whose endpoints lie on the circle. There are infinite chords that can be drawn on a circle. So if you draw a line that goes from edge to edge on the circle, this would be X and Y, that would be chord XY. I can draw another one going edge to edge on the circle. If I call that W and Z, that would be chord WZ. So chord is any segment whose endpoints lie on the circle. Now, a subset of chord is diameter. A diameter is also a segment with length, like a chord. And it's basically a chord that passes through the center point of the circle. There are infinite diameters. So in this picture, B to E is a chord that passes through O. So BE is a diameter because it passes through the center. Now, if we want to find the length of BE, OP is a radius. And we know that BE, a diameter, is 2 times the radius, right? Because any diameter is 2 radii put together. So if my radius is 2 inches, BE equals 2 times 2 inches, which would be 4 inches in length. Remember, a radius has the same length no matter where it's drawn. So if O to P is a radius that's 2 inches, O to B is 2 inches, O to E is 2 inches. All radii will be 2 inches. Okay, number 3, secant. A secant is a line that passes through a circle and intersects it in two places. Infinite secants can intersect a circle. A secant automatically contains a chord. All right, so if we use E and F as intersection points, we can draw a secant crossing the circle at E and F. We can draw another secant crossing at B and C, passing through the circle and continuing outside the circle. Those are secants. So a secant automatically contains a chord. So let's make this point D. I made it a little too far away. That's point D. So we can say that secant line AD contains the chord BC. So the secant is a line, put line notation. Chord is a segment, put segment notation. Every secant contains a chord. And it must intersect in two places, not just one. That's a tangent. That's a different word. Okay, C, figures with multiple circles. Congruent circles. Congruent circles are circles that have the same radii, but not the same center. Congruent circles may overlap. So this is an example of two congruent circles. They're not the same circle. They don't have the same center because one is Q, one is O, but they are the same radius. So example, it says if circle Q has a radius of 27 inches and is congruent to circle O. So if circle Q has a radius of 27 inches and it's congruent to O, both of the radii are the same. So the radius of circle O is 27 inches. But if we want to know the diameter of circle O, the diameter is going to be 2 times 27 because it's all the way across, which is 54 inches. And notation-wise, you can say circle Q is congruent to circle O. Use your circle notation. Pardon?
Didn't we do something similar to this before?
Not with circles. But yeah, we've done congruent figures, definitely. All right, flip the page. Okay, so we just did congruent circles. Now we're going to do concentric circles. Concentric circles are two or more circles with the same center point, but different radii. Concentric circles never intersect. Concentric circles must be in the same two-dimensional space called a plane. So they have to be in flat space. They cannot be in two-dimensional space. All right, circle the letters of the drawings that show concentric circles. Go ahead and do that. Use a pencil. Which of those show concentric circles by the definition? All right, let's see how we did. So A, we definitely have circles of different radii. We got a small one here, a big one here, a big one there. The problem is, in order to be concentric, they have to have the same center point. So this one is not it because they have different centers. Okay, B, we have this center point here, but the new center point of the second one is here. The third one is about here. So they have different centers, but more importantly, this is not concentric because of this point right there. These intersect, and concentric circles cannot intersect. Okay, C, all of those circles have the same center. They don't intersect. They're in a flat plane. C shows concentric circles. Now D, here's the center, so they have the same center, and there are two circles, a front one and one that's coming towards you, and one of them that's flat. The problem is that concentric circles have to be flat in a plane, and this is not a plane. It's a three-dimensional figure, and it must be two-dimensional to meet the definition. All right, let's go on to D, tangency, tangency. Tangent lines is a line that lies in the same two-dimensional plane as a circle, so flat. It intersects that circle in exactly one point. And that one point is called the point of tangency. It's the point at which the tangent line, or any other figure for that matter, intersects the circle. So I can draw a point of tangency at K, and if there's a line that only touches the circle at K, we'll call that italicized L. That is a tangent line. So line italicized L is tangent. And it only touches at one point. So your point of tangency would be point K. All right, let's do a complete. Complete if line AP. Okay, so we have to draw line AP. If line AP is tangent to circle O, then circle O is tangent to blank, and blank is the point of tangency. So if AP is tangent to the circle is tangent to line AP, and in this case, point A is the point of tangency right here. So you can have other figures be tangent. For example, this little trapezoid has a point of tangency at T. So point T would be a point of tangency. It's not a tangent line, obviously, because it's a trapezoid, but it does have a point of tangency. Okay, E, spheres. A sphere is a three-dimensional figure, and we say it is in space. Space is the geometric word for 3 dimensions. It is the set of all points equidistant from the center point in a given space. Okay, so if we take this middle circle and draw in the invisible part, which is in the back, that would be the center point of the sphere. And if I draw a line to the left and to the right, those would be radii, and they are congruent. What makes this a sphere is I can also draw a line straight up to the top, and it will also be congruent. So 3 dimensions of congruent radii make a sphere. Okay, flip the page. And you'll notice I have a lot more pictures because they're really hard to draw. So congruent spheres. Congruent spheres have the same radii, but different centers. Congruent spheres are in 3-dimensional space. Concentric spheres have the same center point, but different radii. So concentric have different radii. They're also in three-dimensional space. Concentric spheres do not intersect. So this is an example of concentric spheres. They all have the same center point, but different radii, and they never actually touch each other. They're nested. I think of it like nested circles that don't touch each other. Okay, F, inscribed and circumscribed. These are words we have used before. A polygon inscribed in a circle. We say that a polygon is inscribed in a circle if every vertex of the polygon lies on the circle. In other words, for inscribed in a circle, it means the polygon is inside the circle. Okay, so looking at this, my polygon is triangle ABC. And each of its three vertices are touching the circle. That means ABC is inscribed in circle T. Inscribed in. All three vertices have to be touching. All right, circumscribed. Circumscribed. A circle is circumscribed about. So circumscribed about a polygon if every vertex lies on the circle. The circle is outside the polygon. So in this picture, ABC is inscribed in circle T, but we can also say circle T is circumscribed about triangle ABC. So you can describe the same drawing from two directions, inside out and outside in. If it's inside out, it's inscribed in. If it's outside in, it's circumscribed about. All right, practice labeling. Identify using appropriate notation. So I want you to identify the center, the radius, the diameter. So I want you to go back through these words and fill them in. All right, I'm going to give you some time to do that.